There we go. So first of all, I realized last night as I was going through some stuff that I missed a really important thing from the first section, and that's this limit right here. This limit is something that's going to appear over and over again, and it's something you're going to have to use to do more limit problems, to do some derivative problems later on. And so this is the limit that you're going to need to know. At this point, it's not a limit that we know how to figure out the value of analytically, okay, or algebraically. We can figure out how to do it using a table or using a graph. I won't waste your time right now having you guys graph it, but if you graph this function, actually first, let's try to do it algebraically. If we plug in 0 for x, what do we get on top? 0. And on the bottom? 0. And if you remember, when direct substitution doesn't work, but we get something like 0 over 0, we might try to manipulate it a little bit, change it in a way so that we can plug it in and it will work. Unfortunately, this is one that we can't really change in a way that 0 can just be plugged in, at least not knowing what we do now. Later on, once we start doing derivatives, we're going to come up with a method that will allow us to do limits like this. So what we want to do here is we want to look at it graphically. I'm going to graph it for you here. Sorry. But from the graph here, you can see that as x approaches 1, then the value of the function, as x approaches 0, then the value of function is approaching 1 from both sides. All right, so this limit here is going to be equal to 1. You could also do that, like I said, using a table. So this limit here is going to be equal to 1. The sine of x over x as x approaches 0. All right. So here's how you're going to use it. There's an example in your textbook. Abdallah came in this morning. He actually asked me yesterday about this question, and I answered it for section 2.2 instead of section 2.1. It was the same problem, just a different question. How would we find a limit like this? Any ideas how we could get started? And I will tell you, we're going to use the limit from the last page. The limit is x approaches 0, sine of x over x. And that's not the right problem, is it? Abdallah, that was an x there, wasn't it? Okay. 2x squared minus x. Sorry. So how could I use that last limit to do this one? Any ideas? Vimal? Sorry. Yes. So if we factor the x in the bottom, and work on your mathematical notation while you're doing problems like this. So we need to keep the limit because we haven't plugged in the value of x yet. So we're doing the limit as x approaches 0. We'll keep sine of x on top, and we're going to factor out the x on the bottom. And what we have left then is 2x minus 1. Okay, everybody follow what I did right there? Now, to make things easier visually, I'm going to split that up into two different fractions. So that is going to equal, and this is another notation thing that's important. This equal sign is important here to show that it's equal to the last thing in the line before it. So that's going to equal the limit as x approaches 0 of, let's just do the sine of x over x first. And when I pull the sine of x over x out, what's going to be left? What's left in the denominator? 2x minus 1. And then on top, there's nothing left, so we'll put a 1 there because sine of x times 1 is sine of x, right? Now, there's a property of limits. We didn't spend much time talking about it, but basically, if you take two separate functions and you multiply them together, then the limit of the product is the product of the limit. So I can take the limit of this one, I can take the limit of this one, multiply them together, and I'm going to get the whole limit. All right, so what is the limit as x approaches 0 of sine of x over x?
1.
That's 1. We just figured that out, right? And what is the limit as x approaches 0 of 1 over 2x minus 1? Well, can we use direct substitution there? Yeah, just put a 0 in there. We get 1 over negative 1. And so we end up with negative 1. Does that make sense what we did there? So we took part of it and we made it look like the limit that we knew, and then the rest of it turned into a limit that we could evaluate using direct substitution. So that's a process that we're going to use quite a bit, where we're going to take something and manipulate it into something that we can use, and we may end up with separate parts that we know and parts that we can do more with. Yes?
Wait, how is the sign of x over x as x approaches 0? How's that going?
Any other questions here? All right, moving on then. We're going to talk about continuity today. There was actually a question on the test that you'll be getting back today about continuity. It's kind of an intuitive concept. We do define it using limits. So mathematically we define continuity using limits. And it allows us to use it in a little bit more ways, in more ways in calculus. So the definition for continuity, the function f of x is continuous at a point, c, and that's when x equals c, if the limit at that point is equal to the value of the function at that point. So basically it's continuous if the limit exists and the limit's equal to the value of the function. So there's not a hole there, well really if there's not a hole there then it's going to be continuous, and that's kind of the idea. Okay, so that's the formal definition of it. We'll talk about it a little bit less formally later. But let's use that definition here real quick just to show that, to show whether or not this function is continuous at 0. So if I want to know this function is continuous at x equals 0, to do it formally by the definition, what do I need to show? Did you guys get that written down? Did you guys get this written down? Those of you that wanted to write it down at least. This definition is in your book. So I want to show that the function absolute value of x, so that's going to go in here. I want to show that the absolute value of x is continuous at c when c is 0. So I would put a 0 where I see the c's. I would put the absolute value of x where I see f of x. Does that make sense? So I want to show that the limit as x approaches 0 of the absolute value of x is equal to the absolute value of 0. If that's true, and I'm going to put a question mark above the equal sign right now because we don't know for sure that that's true yet. If that is true, then it's continuous there. It's continuous at that point. And all we're testing right now is continuity at a point. So we just want to know at that point is it continuous. What is the limit as x approaches 0 of absolute value of x? 0. And what is the absolute value of 0? 0. They're equal, so that means that it is continuous. Just a quick tip. If you can use direct substitution to evaluate a limit at a point, then it is continuous at that point. Because direct substitution is evaluating the function at that point. So anytime you can use direct substitution, that means it's continuous. If we had to use algebraic methods to use direct substitution, then we're going to have to look into it a little bit more closely. Okay. Another one here. So if we wanted to show that the function sine of x over x is continuous at 0, we would need to show that the limit as x approaches 0 of the sine of x over x equals the sine of 0 over 0. Now, knowing what you know from previous problems today, the limit on the left side is 1. The value of the function at 0 does not exist. It's undefined there, right? Because you can't divide by 0. Is 1 equal to undefined? Okay, that's not a trick question. So it's not continuous at x equals 0. So this is a function. It's actually it's a smooth curve, but it's not defined at 0. It's actually not even part of the domain, so it's not continuous at that point. Does that make sense? Pretty intuitive, I think. So there's 4 types of discontinuity that we're going to talk about. You've probably seen at least most of these. One of them is a removable discontinuity. We saw that in a function over the last couple of days, and we'll look at one of those. Jump discontinuity, infinite discontinuity, and oscillating discontinuity. So here's a picture of all four of those. The first one right here, and it's kind of hard to tell, but this is a closed circle right here. That's a closed circle. So at x equals 0, this function's actually continuous. It's the only one up there that is continuous. The second one, again, it's hard to tell, so I'll draw it in there, has an open circle. So what kind of continuity or discontinuity would that be of the four that I just listed?
Removable.
That would be removable. Why would you say it's removable?
Because it's all the points except for that one point.
Yeah, and what could we do to make it continuous there?
Just put that one point.
Yeah, so a removable discontinuity is a discontinuity that we can just put a point in there and then it's continuous. All right, so basically that means that the limit exists, but the value of the function does not equal the limit. All right, so that goes back to the definition of continuity. If you have a limit, but it doesn't equal the value of the function, then it is removable and we can fix that. Same thing with this other one. The function is defined as such. It has a hole in the line, but then it's defined somewhere else. That's still a removable discontinuity because if we change the value of the function at that one point, then it is now continuous. Does that make sense? Okay, how about this one right here? Doesn't really matter where the hole is. There's a hole here and filled in here. What kind of discontinuity would that be?
Jump.
That would be a jump. It's a very technical term because the value of the function is basically because the limit on the left is not equal to the limit on the right. So the values approach one number from the left and it jumps to another number as you go to the right. So that would be a jump discontinuity. How about the one in the middle here? Remember the third one? Infinite. So this is one where the limit from the left is infinite, the limit from the right is infinite, and even if you want to try to say those two infinities are equal to each other and the limit exists, we would not say that it's continuous because it's not defined at 0. So it doesn't have a value at 0. So that would be an infinite discontinuity there. And then the last one?
Oscillating.
Oscillating, yes. This is the function sine of 1 over x. And so what we're doing here is we're getting close to 0. We're plugging in numbers really close to 0, and we're getting numbers that are infinitely big, really large. And it's just oscillating back and forth between -1 and 1 faster and faster. So this is an oscillating discontinuity. Those make sense? Think you could recognize those at least on a graph, if not in a function? Typically the jump discontinuities are going to happen if you have a function like the integer function, like we talked about the other day, or more often you're going to see them in piecewise defined functions. Infinite discontinuities you're going to see a lot with vertical asymptotes. The removable discontinuities you'll see a lot of times when you have polynomials where part of the top can reduce with part of the bottom. Then you usually end up with holes in the graph with removable discontinuities. Oscillating you really only get with trig functions. Any questions about those? Okay, cool. So removing discontinuity. So we can write what's called an extension of a function, which would make a discontinuous function continuous. Which type of discontinuity would we be able to do this with? Removable, yeah. So with a removable discontinuity, what we want to be able to do is redefine the function so that it's the same everywhere else, but we redefine it at that point of discontinuity so that it's continuous there also. This is a function we've seen quite a bit, x squared minus 1 over x minus 1. I like using the same one over and over because we're not talking about the algebra here, we're talking about the calculus. And this is a good example here. So we know that this function is the same as x plus 1 times x minus 1. over x minus 1. And if we were to cancel this out, we would be getting rid of a discontinuity at x equals 1. So the function itself has a hole at x equals 1. So if we wanted to make it continuous there, what could we do? How could we rewrite this? And let me say this, we don't want to rewrite it as x plus 1. And the reason is we're not extending that function, we're just writing an equivalent function to its extension. So the extension is going to include this as part of the function. So how could I write a function that has this as part of it, but it's continuous? See where I'm going with this? Piecewise function. So we'll define it as x squared minus 1 over x minus 1 for everywhere that x is not equal to 1. But then what about when x equals 1? What do we want the function to equal so that we make it continuous? Cole? You could do that actually, but what is x plus 1 when x equals 1? Yeah. So this function is an extension of the function, which means that we take the original function and we add to it. And so when we call it an extension, we don't want to change it. We just want to redefine it. Does that make sense? This function that we just wrote here is equivalent to the function. Equivalent would be 3 lines. It's equivalent to the function x plus 1. But this is the extension of this function. This is not. Kind of a subtle difference. You will not be asked about something like that on the AP test. You may be asked to remove a discontinuity, but you won't be asked what is an extension of a function or anything like that. Okay, I think this is kind of an interesting definition. The definition of a continuous function, so we're not talking about continuity at a point, but just a continuous function, is a function that's continuous at every point in its domain. And strangely, this definition includes functions like f of x equals 1 over x. 1 over x is a continuous function. Why is that strange that that is called a continuous function? It's not defined at 0. All right, so it's not continuous at 0. It's not continuous at the point equals 0. So why does that fit this definition?
Because its domain doesn't include 0.
Exactly. Its domain doesn't include 0. So it's continuous everywhere in its domain. That makes it a continuous function. Seems kind of weird, doesn't it? We will use continuous functions a little bit, or at least the idea of continuous functions, but more often we're going to use the idea of continuity on an interval. So before we get to that though, let's talk about composites. You guys know what I mean when I say composite? Composite functions?
So like f of g of x.
Yes. So a composite function would be like f of g of x. So for the functions that I gave you here, what would be the composition f of g of x?
Sine of the absolute value of x.
Sine of the absolute value of x. Okay. And if I said g of f of x, then it would be the absolute value of the sine of x, right? So you guys know how to compose functions. In fact, you guys showed me on the test that you were pretty decent at that. So one important property to understand about continuous functions is that when you compose continuous functions, you get continuous functions. Sorry, a little stutter there. The sine of x is continuous. The absolute value of x is continuous, which means that the sine of the absolute value of x is continuous. And this even works with functions like 1 over x. You just have to be sure that you take into account domain issues. So we talked quite a bit before the first test, and I asked a question about it. When you compose functions, you need to be able to know what the domain of the new function is, and that depends a lot on the domain of the inside function. and then the domain of the composed function, the domain of the function you end up with. So it can be restricted in two different ways when you compose functions. So everywhere that function is defined, and every point that's in the domain of that function is going to be continuous as long as the original functions were continuous. And that's an important idea. You can add, subtract, multiply, divide continuous functions and get more continuous functions. All right. Now, why do you think I have an asterisk next to divide continuous functions? Let's say I have the continuous function f of x equals the sine of x, and g of x equals the cosine of x. These are both continuous, right? So we would have to throw in a third function, which would be h of x is 1 over x if I want to write it as a composition. But I can compose these functions in a way where I get another function, we'll say r of x equals sine of x over cosine of x. And I just said I can add, subtract, multiply, divide continuous functions. These are both continuous functions, and get another continuous function. So why do I have the asterisk here next to divide? Yeah, the domain changes. So in this case, the domain is not going to include values where the cosine of x is equal to 0 because it's going to end up in the denominator. So we have a domain change where we don't have values included in this continuity at pi over 2 plus n pi. Does that make sense? Yes?
Why did you have h of x is equal to 1 over x?
This idea here, continuity on an interval, is much more useful in calculus than just the idea of continuous functions. We need to have an idea of what it means for a function to be continuous on its domain. But this continuity on an interval is going to allow us to actually do stuff. And so this is far more important. So a function is continuous if and only if it is continuous at every point in the interval. It would not be possible to take some function on an interval and test every possible point. And so this is where the idea of continuous functions is useful. If you can recognize functions as being continuous or discontinuous, or recognizing where we might have continuity problems with a function, that's a good thing to know, because we can't test every single point. There's just infinitely many of them. When we're talking about a closed interval, then if we want to say that the function is continuous at a point on the end of the interval, then we can't talk about the limit as just a regular limit, because it's not going to have a limit going to the left, because we're not looking to the left of the interval. So the left endpoint of an interval is continuous if the limit as you approach from the right of that value is equal to the value of the function. So what that means is, if we're looking at a closed interval on a function, so let's say we're going from a to b, including a and b, we would say it's continuous at a if the value of the limit approaching from the right is equal to the value of the function. Does that make sense? If there's a hole there, or if it has a different value than the limit at that point as you approach from the right, then it's not continuous at that point. What we don't care about is what happens over here, because that stuff's not on the interval. So nothing that happens to the left of the point of A matters on this interval. And that's why this limit is restricted to coming from the right. It's similar for the right endpoint. So if we're talking about the right endpoint B here, and we want to see if it's continuous there, what change would we have to make here? Obviously, we're going to change the A's to B's, but what else?
Negative.
Yeah, we would have to approach from the left. So this would be X approaches B from the left, or negative B. Well, not really negative B, but you get it, right? Okay, cool. So I want to know, is this function 1 over x continuous on the closed interval from 0 to 1? We already said that 1 over x is a continuous function. So are the points from 0 to 1 in the domain of this function? If all the points are in the domain of the function, then we don't have any worries. We just say it's continuous on that interval, and we move on to the next thing, which will be far more exciting than what we just answered. Are all of the points from 0 to 1 in the domain? No. The right endpoint we don't need to worry about, right? Correct? Because at the right endpoint, one's in the domain, it's talking about a continuous function, so we don't need to worry about the right endpoint. Yes?
I'm confused why it's continuous if it's not in the interval.
If you remember the definition of a continuous function, not continuity to point, and we're not talking about continuity on the interval yet, but just a continuous function means that it's continuous for all points in its domain. So since 0 is not in the domain of 1 over x, then we don't have to worry about saying it's not a continuous function there. Does that make sense? Okay, but what we do need to worry about, since 0 isn't in the domain, is we need to check that point. So if we want to know if it's continuous at 0, which is the only place that we might have an issue when x equals 0, we want to show what? Anybody think they could set up the equation to show that it either is or is not continuous? Or you just want me to do it? Okay, I'll do it. Which way are we going to approach 0? Okay, we want to approach it from the right. So that's kind of the main thing here. We want to look at the limit as x approaches 0 from the right of our function, so of 1 over x. And if that is equal to the value of the function at 0, which is 1 over 0, I'll go ahead and plug that in, then we're good, right? What is the limit as x approaches 0 from the right? It's infinite, right? So 1 divided by 0 is either going to be positive or negative infinity depending on if we're to the right of 0 or to the left of 0. What is 1 divided by 0 here? Are we coming from the right or the left in this case? This is just the value of the function. It's undefined, right? Now, even if we were just coming from the right, we would have infinity, and infinity is not equal to infinity, or at least we don't know that it is. So either way that we approach it, it's not going to be continuous there. So on this closed interval, then this function is not continuous. Could I rewrite that interval just with a slight change so that I have an interval that is continuous?
Two parentheses instead of the close on the 0.
Exactly. So if I just change the bracket here on the 0 to a parentheses, now we're not including the point 0, and it's going to be continuous on that interval. Does that make sense? Alyssa, you look like you're having fun. More continuity. Okay, I was being sarcastic, actually. Is f of x equals 1 over x a continuous function? Yes. Is f of x equals 1 over x continuous on that interval? And that's a different interval than we just did, but you know that it's not because it includes 0. Yes.
Okay, for the first bullet point,
Yes.
is that just referring to it like as a broad term?
Yes,
Like you
just-
assume,
Yeah.
unless it gives you like an interval?
Correct.
Okay.
Okay, so the point of this slide here is to hit home the difference between a continuous function and a function that's continuous on an interval. Like I said earlier, this is going to be more useful to us in a lot of ways than this is. This allows us to interpret this, though, more easily. So you need to understand when we're going to have functions that are continuous, and you need to understand when you might have problems with continuity. So even though 1 over x is a continuous function, you also recognize that when we're talking about intervals or at a point, we're going to have problems at 0 because it's not defined, it's not in the domain there. Yes?
Can you give an example of a continuous function?
I said I would talk about continuity on a more informal level. Basically, if we're talking about continuity on an interval, let's say we're looking at the interval from a to b. I will very often use the letters a to represent the left side of an interval and b to represent the right. So the function takes on some value. Here at a, we'll call that f of a. And it takes on some value at b, we'll call that, what do you think we should call that? Yeah, you guys are smart. Let me fill that in so we avoid any confusion there. Those points are defined there. if the function's going to be continuous on that interval, if you take a pen or a pencil or your finger on an iPad or whatever, if you can draw it from f of a, oh man, I messed it up. If you can draw the function from one point to the other without lifting your pen, or without lifting your finger, or without lifting your pencil, then it's continuous. It doesn't matter if it looks crazy and has points and waves and goes below the axis or whatever. It's continuous if you can draw it without lifting your pen. Okay? Obviously, if we're talking about functions, we're not going to have things that look like this because
It's not a function.
yeah, it's not a function. A vertical line test. So we have some x value c here that has multiple values, which is what you were trying to say, I think, right? Okay. So informally, we could say that a function is continuous on an interval if you can draw it without lifting your pencil. And that's actually a really good way to think about it because it'll give you an idea of when you wouldn't be able to do it. So you're going to have discontinuities at infinity. You're going to have discontinuities when you have to jump values. You're going to have discontinuities when you have a hole because you have to lift it to make the hole. Okay? Cool? Okay, intermediate value theorem. This is probably the most important thing we're going to talk about today, besides the whole idea of continuity, which was everything else we talked about today. So the intermediate value theorem is a big theorem that tells us why a lot of stuff works in calculus. And I'm going to recreate that picture I just had here. So let's say we have some function graphed on the y-axis on the interval from a to b, and the function takes on some value at a, we'll call it f of a. It takes on some value at b, we'll call it f of b. So what the intermediate value theorem looks at is the values of the function between f of a and f of b. And what the intermediate value theorem says is that if the function is continuous on the interval, then what has to happen? What do you think? So if I draw the function, I'm going to draw it in blue here. I'm going to start at f of a and go to f of b. What has to happen? Lewis? It has to hit every y value from f of a to f of b. So as it goes from as we go from a to b on the x-axis, as long as the function is continuous, at some point that function is going to take on any particular value that you pick between f of a and f of b. So if I pick any y value here, we'll call this f of c. There's not going to be any place that I skip over that value, meaning at some point the function has to equal f of c. Okay, and that's only true because f of c is somewhere between f of a and f of b. So I can't have a continuous function that looks like this and does not take on the value f of c, because that would not be a continuous function, right? You guys agree with that? Now, this seems very intuitive, and it is. It has a name, the intermediate value theorem. You need to get to know that name, because I will tell you that on the AP test and also on my tests, you will use the intermediate value theorem as an explanation or justification for your answers for certain types of problems. We will abbreviate it. You don't have to write out intermediate value theorem. If you're on the AP test and you write IVT, they know what you're talking about. It's a big enough theorem in calculus that you can abbreviate it and everybody knows what it means. All right? And it's a very simple idea, but it's a very powerful idea. Any questions about that? Okay, so at this point,